Okay, welcome back. We're continuing our discussion on week 2 materials. So to start off, I guess the order really isn't matter in this particular case. So we're going to start off our discussion with valence electrons. Okay, valence electrons. Now I will bring back the periodic table in just a minute, but let me walk you through what are really valence electrons. As I said, if this were to be a 400 or 500 level chem class, I might give you even more details on every single concept I have taught you so far, but for the purpose of our class and how it meets your requirement for completing the course, I think what I'm going to explain to you now is just sufficient. Okay. Let me write it in simple terms what this valence electrons really mean. Okay. Valence electrons are the only electrons, okay, the only electrons available for use. Okay. Now what that use is, we're going to talk about it. Okay. Available for use. Okay. That means, okay, electrons typically can be lost or gained. Okay. Okay. So whenever an atom, okay, okay, the next bullet point is an atom can gain, okay, or lose electron or electrons. Okay. Now let me stop here for a second and explain something. Okay. Even though an atom might gain or lose electrons plural, it happens in a systematic way. It doesn't mean if let's say an atom can lose 4 electrons, it doesn't lose all 4 in one go. Okay. It loses one at a time. Similarly, if an element has to gain 4 electrons, even that happens in a consecutive, in a stepwise manner. That is, it can only gain 1 electron at a time. Okay, the first electron that it's gained must be added to the atom before the second one can be added. Okay, now that in itself is what gives each of those elements that you saw its own identity. Okay. Now, okay, so that brings us to the second idea. We learned the name or the word orbitals, right? Okay, valence orbital. We're going to add that prefix valence to the word orbitals. Okay, or I'm going to put this in bracket with a different color because you could have technically a valence orbital or orbitals. Okay. All right. So a valence electrons are the only electrons that are available for use. That is, I'm going to go back and write it in brackets here. Gain or lose. Gain or lost. That's the purpose of use. When I refer to use, that's what I'm really referring to, is that atom can gain or lose electrons. Okay. Now I'm going to bring back the periodic table before we continue our discussion. So let me delete these and bring back my periodic table. All right. If you notice, okay, actually I'm going to get this. Okay. Let's write, while we are here, let's write the electronic configuration, say, for beryllium. Now, if you have that PowerPoint that I showed you all, now I'm writing the electronic configuration for beryllium. Okay, it will be 1s and 2s, and that's it. That's where we stop. Okay, beryllium's got an atomic number of 4. Okay, that means it's got 4 protons and 4 electrons. Now keep in mind, when we do our electronic configuration, the sole purpose is just to focus on the electrons, right? So let me get a different color here. Okay, so I can pinpoint, and so this is what it really is when it comes to when we write electronic configuration, we give importance to the electrons. So we need 4 electrons, and we know S can hold 2, so 2. Well, we only got 2 more left, so we add the 2, right? Now if you keep in mind, let me give another color here, maybe perhaps a blue. Okay. Now whatever the last orbital or orbital set, which we will come back to with a different example. Okay. Now if you see, in this case there are no other 2's, it's only the 2s. Okay. This is the last orbital in the right up, so this right here is the valence orbital, not orbitals, because there's not one more. We will see, I'll show you another one just to see what that difference is. Valence orbital, not orbitals, right? And how many electrons does that, the last orbital in the right up usually is your valence orbital, means that element and the atom that's contained in the element can only lose or gain 2. Now we will decide eventually, okay, some elements cannot ever lose, some can only gain. Okay, I will give you that list, but I want you to first understand the idea of valence orbital and valence electrons. If you don't have a very good understanding of that, then anything I would say building on that is not going to be helpful. Okay, now let me get another color here, maybe a red. Okay, now remember I said that those Roman numerals have a significant value in a periodic table, and I did not just say that for saying it, I really meant it. Okay, now if you come back here, we are looking at beryllium, so it's in this column right here. As I said, just focus only on the Roman numeral for the remainder of the course. Don't worry so much about the integer, because the Roman numerals really have a meaning that can easily be understood than the integers. What do you think is a Roman numeral? If I write it out, it's 2a. Okay. What do you think that element's valence electrons are? Well, that's 2 right here. So what that means is, let's say if you write down the electronic configuration, say for beryllium, magnesium, calcium, strontium, barium and radium, you will see that it may not be 2s, okay, but it will always be 2 valence electrons. Okay, so that means, let me tell you a secret now. If you notice, the periodic table is made up mostly of metals. Okay, these are metals, these are metals, these are metals. These are called the alkali metals, the first column right here, except hydrogen, of course. A second column is known as the alkaline earth metals. These sandwich metals are known as transition metals. Of course, I will come back to this in a detail, so you don't need to think, oh, he's rushing through. No, I'm just telling you what I know right away. So these are the transition metals. These are the rare earth metals. So if you see, and if someone asks you a general question, hey, is a periodic table made up of mostly metals and non-metals? The answer is metals. Okay, so let me write a key term here, metals. I don't know of an exception, but metals always, when I say always, I mean it. Always, let me get my eraser right here. What I meant to say was always lose electrons or electrons. Okay, I don't think I'm quite happy with my handwriting here, so let me go back and erase this part right here and rewrite this. Take my time. Always lose electrons. On the contrary, I'm going to get a different color. Okay, black. These are non-metals. Okay, preferably over here. All these folks right here. Okay. Don't worry about, I did write into the noble gases, but that's really not everything you see in the black are non-metals. So I'm going to be consistent with my color. Non-metals mostly, we would never go into the exception in this class as we're only in a 150, mostly accept or gain, accept electrons. Okay, so that means, what does it mean in terms of everything I have told you so far? Okay, so if it's beryllium, well, beryllium is a metal, right? So if I ask you a simple question, hey, how many maximum number of electrons, that's the key word here, okay? How many maximum number of electrons that beryllium can lose, you will know right away that it can only lose 2. It cannot lose 3, it cannot lose 4, it cannot lose 1, but it can only lose 2, okay? That means it can lose all of the 2 electrons available in the valence. So when I ask you a specific question, which orbital from which those 2 electrons are lost, you must be able to say 2s, which means you must be able to write the electronic configuration in the first place. Does that make sense? Okay, so let's get this back, delete, and then bring the periodic table back. Okay. Now, if you notice, if you didn't believe me for my word, well, let's just do magnesium. Okay, let's get our red color back. Okay, let's do the electronic configuration for magnesium. And what's the atomic number of magnesium? It's 12. What does that 12 means? 12 means it's got 12 protons and 12 electrons, right? Very good. Now, if you remember beryllium from the previous screen, we had 1s2, 2s2. Let me write that down somewhere here so you can compare it to see those Roman numerals do have a meaning. Okay, now that is never really taught, or people never really understand it, but learning it this way, you really see the significance between everything that's happening around us. All right, let's go change our colors, maybe get a black, and let's write the electronic configuration. Now, magnesium is in the 3rd row in the S band. That means we got to go get the others first filled. So 1s, 2s, 2p, and 3s, right? Okay, that looks like a 35. Let me erase it, you know. Okay, that looks more like a S to me. All right, now let's get a different color, maybe a blue. Okay. All right, now there's 12 electrons. As I said, you always fill from the left to the right, and you have to take into account how many maximum it can hold. Well, the S can hold 2, the S can hold 2, the P can hold 6. Now, this is what I was saying earlier. So if you say you add 2 plus 2 plus 6, well, that is 10. How many more do you need to get to the target of 12 electrons? Well, we know right away we need 2 more, right, to get 12 electrons, right? That means we got to put 2 right here, right? If you compare this right here and compare this right here, what do you see is common? Well, if the Roman numeral has to be 2, and that's one way to check if you got the right configuration, is, well, because we're going down the column, well, obviously it's going to go from beryllium is in 2nd row, this was 2nd, and magnesium is in the 3rd row, so this is making sense, it's 3rd row. But what makes more sense is the S2, because the Roman numeral is 2a. That means, and we know for fact that beryllium, magnesium, calcium, all of these, anything that I did not show you within that black band is a metal, right? That means magnesium, if you can come back and write, magnesium can lose max of 2 electrons. Does that make sense? So let's do a different example where we start to make sense of this. Okay, so let's bring our periodic table back. Okay, and let's choose, I guess it really doesn't matter what color. Let's pick oxygen. Okay, let's pick oxygen, and if you notice its atomic number is 8, and oxygen is a non-metal. It was within that black band I drew. So it's not that difficult to remember which ones are metals, which ones are non-metal. It really is just, there's only a little bit of non-metal, but the most of the periodic table is non-metal. Well, oxygen is in the p band in the second row. That means we have 1s, 2s, and 2p. That's where we end our destination for oxygen. Now oxygen's 8, that means it's got 8 protons and 8 electrons. But keep in mind, whenever we work our periodic table, whenever we write our electronic configuration, we're really only worried about the electrons. I think I've mentioned that a few times. So that means we need 8. So if you put 2, 2, and 6, and how many do we need? 4. Right? Now this is what I meant by valence orbitals. Now let me get a different color because this is a really important concept. Okay. In all those 2 examples we saw of beryllium and magnesium, we only had the last one had just a single 3. Okay, didn't have a combination. But here, however, okay, there's the last one is 2p. You look for, hey, is there another 2 that goes with it? Yeah, I sure do. There's 2s. And so it's not just a 2p4 that's the valence orbital, but the valence orbitals are 2s and 2p. Now the question is, hey, if you lose an electron, where do you first lose? Well, obviously you lose first from the p's, and when you gain, the gained electron goes to 2p4. I'm going to show you precisely what I meant by that. All right. So if you come back to our beautiful Roman numeral, it all makes sense, right? 6a. How many electrons do we have in the valence? 6. 2 plus 4 is 6. I don't think anyone will disagree with me right there. 2 plus 4 is 6. I'm not sure why my pen is acting up. Okay, 6 electrons. So the Roman numerals, what they are really telling you is how many valence electrons you have. Now in case of metals, whatever that Roman numeral is, that's how much it can lose. Whereas in the case of a non-metal, it's slightly different. It doesn't gain 6. 6 is what it already has. Okay, so how many can it have? Well, it always have to do with how much does it need to get to this magic number of 8. Okay, we're going to do another example. So if you are not paying attention or didn't understand it, I'm not going to say that's it, that's enough, we're going to move to it. No, we already have 6. Okay, we have 6, but to get to 8 we need 2 more. Okay, 2 needed. Okay, that means oxygen can only accept 2 more electrons. Okay, this is a difference between metals and non-metals. Metals accept electrons, non-metals give up or lose electrons, and how much they lose for metals depends on the Roman numeral. So if it says 2, that means it can lose 2. Whereas for non-metals, 6 does not mean it's going to lose 6, because non-metals are supposed to gain, and they always have to get to 8. So oxygen's got 6, and it can only accept 2 more electrons. Okay, so let me get rid of this and come back again. Okay, so let me explain something very important with the same oxygen case. Okay, so oxygen, we wrote the configuration was 1s2, 2s2, 2p4. Okay. Now, this is a single oxygen element, but we all do something every day, which is breathe. Okay. We breathe. Okay. The air that we breathe got oxygen in it, and that's not O. That's not O. That is O2, right? That's O2. This is what we breathe. Okay. For this to really happen, each oxygen must have 2 more electrons. It has to go into an ionic form, which again, I don't want to go too far into this concept right here, but I do want to emphasize this. This already has, we asserted the fact that it's got 6, and to get to a stable 8, it needs 2 more. So let's say it has taken 2 more electrons. Whenever a atom in an element accepts electrons, we give it a negative charge, which is contrary to what we do in our daily life. When we lose money, right, we give negative. When we gain money in our bank account, we give it positive. But chemists always think opposite to the rest of the world. In chemistry, losing is positive, gaining is negative. Okay, because oxygen is a non-metal and it has to gain 2 more to get to the stable configuration of 8, that means when it gains 2 electrons, you write it as O2 minus. Let me explain it with a different color so you can see what I have done different. If oxygen has to gain 2 electrons, then it has gained 2, and you just write the minus ones, which means the minus indicates its gain. Actually, let me get my blue. Okay. The minus indicates gain. Okay. The 2 indicates however many electrons that's got, gained 2 electrons. So you would wonder, why can't you just be with this rest of the world, which says minus means losing, plus means gaining? No, I think chemists like to think otherwise. Okay, so it's O2 minus. That's the way you say it. Now, what does that configuration look like? Let's come back and write here. O is as usual. O2 minus is 1s2, 2s2, 2p6. Now, both 2s2 and 2p4 are valence orbitals. Okay, you cannot say that only 2p4 is valence, it's both of them, but 2p, it's at the end of the 2, so the incoming 2 electrons go into the p first, not s. Okay, so let me get my red color back. Okay, all right, so let me get my red color back. This is the correct configuration. I have students write, let me get my maybe a black so I can write it and then say which one is incorrect. Okay, so I'm running out of space here. O2 minus, I have students write 1s2, 2s4, 2p4. Now, for anyone that has done any electronic configuration practice, you would probably agree with me, well, S can only hold 2, so how do you even add 4 in the first place? Now, do you see the connection that when I say yes can hold 2, means you cannot have this is, I'm going to go back, get my red color. Okay, that means this is incorrect way of writing, that is the correct way of writing. Please do not mix up O and O2 minus. Students do that all the time. They're not the same. Okay, they're 2 different things. Okay, so let's go ahead and do some practice in the next sequence. So I'm gonna pause the recording here.